Good evening. I am Henk Broer. I am chairman of the Johan Commelin Foundation for Mathematics. And I bid you all very welcome to this lecture. And I also bid the listeners to the live stream welcome. Johan Commelin worked in Groningen between 1695 and 1705, 10 years. And Daniel Commelin, his son, was born here in 1700. Both were international scientists, member of all the European academies. And normally, when the sun shines, you can see them both on this window, but now it's dark, so you have just to believe me. It is my great pleasure to announce the speaker of tonight. It is Johan Commelin from Utrecht University, and he speaks about, can machines do mathematics? This is an intriguing question that deserves our utmost attention. I thank you for being here, for being available at such short notice when the originally planned speaker, Johannes Schmid, suddenly and unfortunately had to decline for health reasons. Johan will now be introduced by Bart Verheij from the Johan Commelin Institute.
Thank you, Henk. So it is also my pleasure to welcome you all, and especially Johan, for stepping in for this very fascinating topic. And I discovered when we had this very pleasant preparation meeting that you actually are investigating and experiencing what my question was when I left mathematics. And that was, what when there is doubt, when maybe there is a mistake, when it becomes so hard that we with our human skills, well, don't know anymore what is right. Did we do it right? And yes, I will try. Is this close enough? Okay. Very close. Johan, is this? Oh, okay. Look. Okay, so is this really better? Johan studied mathematics in Leiden, his bachelor and his master. Then he went on to do his PhD in Utrecht, Nijmegen. And the title of his dissertation is nice to actually say, because that shows the kind of mathematician that he is. Let me read it. On L-adic compatibility for abelian motives and the Mumford-Tate conjecture for products of K3 surfaces. Well, that sounds like hardcore arithmetic algebraic geometry. And he went on then to do a postdoc in Freiburg in Germany, and then another postdoc in Utrecht. But Freiburg was transformative in his career, because that is, if I understood correctly, where you started to really work with the proof assistant Lean. And you were actually given the freedom to really invest in that and to follow your heart. And it turned out to really transform what you were doing, and you are still doing that, especially also by work on the formal verification of a very difficult proof by Peter Scholze, but I guess that you will be speaking about that more also to this audience. And that led you to now be an assistant professor in Utrecht, where you are actually continuing your mathematics research, where you also supervise 3 PhD students. And most of your time you are spending actually on the proof assistance work in the Math Lib initiative, where you are the director and leading a team of 12 people, formalizing mathematics in a machine-readable format. And that brings us to this connection, well, this puzzle, how to know what is right and what is wrong in mathematics. And that's the start of what you are speaking about. And it's in a sense the opposite of what we now see in artificial intelligence. Because there, the generative tools that now are transforming all our lives, they are by nature, actually by design, guessing. They cannot be checked. So this balancing of, let's say, the generative hallucination of today's AI and the checking that you do with your Lean tools is in a sense the background, I think, of what you are speaking about. and also will change probably the future of mathematics and how we experience that. I don't know what the audience thinks of this, but I think we will be inspired by what you are saying to us. Please, Johan.
Yeah, thank you so much for the very kind words and for the opportunity to speak here. I'm working with the title Can Machines Do Mathematics? And as Bart already alluded to, there are several components to this. There will be quite a lot of AI tonight, but then there is also Lean, this formal verification. So let's dive into it. So 3 years ago, in 2022, November, ChatGPT was released into the world, into the wild, and sort of overnight, this completely changed what people thought of AI and what computers could do. And we discovered that, well, everybody who needs to write a Sinterklaasgedicht can now just ask ChatGPT and it will write something that is way better than you would ever do in the 5 minutes that you have left to write the poem. You could suddenly converse with a computer, and before that there were like these chatbots, but this completely blew everything that came before out of the water. But we also discovered if you asked it to multiply 2 3-digit numbers, then it would just fail miserably because it would make a plausible guess. Probably the answer had the correct number of digits, but that was the only thing you could say about the answer. Whereas a pocket calculator from 1972 had no trouble at all with calculating computing the product of 2 3-digit numbers. These were the kind of things that we ran into. Like you ask it, if 5 machines take 5 minutes to build 5 widgets, how long does it take 100 machines to make 100 widgets? Anyway, so we fast forward 3 years, just 3 years, and now we suddenly see AIs winning medals at the International Mathematical Olympiad. Some AIs won silver, others won gold. And moreover, later in the year, AIs are actually suggesting key ideas in research papers. So in the time span of 3 years, we moved from AIs being terrible at multiplying 3-digit numbers to AIs suggesting key ideas in mathematical research. And the question is, what happened? So that's what we want to dive into tonight. And we'll look at this story. It actually starts quite some time ago. So I want to take you back to 1967, when Nicolaas de Bruijn, some of you may know him and have met him even. Unfortunately, I never had the opportunity to meet de Bruijn. But in 1967, he had this extremely ambitious and avant-garde idea of writing a computer program. He called it Automath, that knew the rules of logic. And so if you wrote your mathematics in a very strict manner, this computer program would be able to check line by line whether the line it was reading right then followed by the rules of logic from everything that came before. And so in this manner, if Automath read your mathematical text and it said there are no mistakes, then you would have a very, very high guarantee that there were no mistakes. Basically, the only thing that could have happened was there is a bug in Automath, or some cosmic background radiation flipped a bit in your computer, and so the answer became yes, while it should have been no. Both of these are very small because the Automath program was written very carefully, was checked by many people, it was a relatively short program, so the chances of bugs hiding there that would let these logical mistakes happen were way, way smaller than the kind of mistakes that normally show up in mathematical research. And all of this started in the Netherlands, in Eindhoven. actually pretty amazing. So I'm quite proud of that, even though I didn't play any role in it. And then, so, wait. Somehow it's skipping forward 2 slides. So then, a student of De Bruyn, roughly 10 years later, Van Bentham-Jutting, translated all of Landau's foundations of analysis into automath. And so he took this whole book and translated all of it into this really strict computer language and checked that it was correct from beginning to end. And basically nobody noticed, and everyone who did notice thought, okay, this is absolutely not what we should be doing in mathematics because it's painstakingly slow and yeah, it's just not worth the enormous time investment. But actually, I believe it was a very visionary idea and decades ahead of its time. So now we take another jump in time. And I want to show you a successor of automath, because automath had a lasting influence on many similar types of computer programs that followed it. And one of the most recent ones is the lean proof assistant, which started its development in 2013. And it's the most popular system in use right now among mathematicians. And what you see here is a screenshot that I took. On the left-hand side, you have the computer code written in Lean, and on the right-hand side, you see what Lean reports back. So you have a proof of the fact that there are infinitely many primes. Let me see. Okay, so over here you can see it says the existential quantifier. So what it says is we have a natural number n, and for every natural number n, there exists a capital N that is larger than the small n that we already had, and such that this capital N is prime. So there's always a larger prime number. In other words, there are infinitely many primes. And after that, this is somewhat hard to read because it's written in this very strict programming language called Lean, but these are commands, and you can see it's talking about the factorial, so that somehow is good because that might show up in a proof that there are infinitely many primes. You need to multiply a bunch of numbers together. Either you multiply a bunch of prime numbers or you just take a factorial and then you multiply some extra numbers. Anyways, on the right-hand side, you then, where is my pointer? On the right-hand side, you see what Lean is thinking along the way. And so we're halfway through the proof. The cursor is on line 14, and it says, okay, you need to prove 2 things. You need to prove somehow that a p that you constructed is larger than n, and you need to prove that it is prime. I won't really go into further details, but this shows you that it's a very strict language. At the same time, there are recognizable symbols, and you can read this statement and recognize that it says, okay, for every natural number n, there's a larger number that is prime. So that's good, that it's, the important parts are readable. The statements that you want to try to understand, like, is this actually the statement that I care about? And then you can learn how to read the proofs, and you can inspect them interactively using this Lean talking back to you on the right-hand side. So that's an aside on the Lean proof assistant, which is one of the sort of grandchildren of automath. 1 second. Yeah. Okay, so then in 2020, the Fields medalist Peter Schulze was stuck with a problem. He'd been working for more than a year on a very complicated proof in a new branch of mathematics called condensed mathematics. And this proof was of fundamental importance because it proved a key theorem that allowed him to do many other things in condensed mathematics, and if that one proof had a mistake, then everything he built on top would just collapse. So he'd written this up in lecture notes, and many people around the world were studying these lecture notes, but then he asked them, did you also read section 9? And the response he got was basically, no, that looked really intimidating and complicated, so we skipped section 9. And the sentiment that he read between the lines was, well, we gave you a Fields Medal, so from now on you will never make mistakes again. He didn't really like that, and he knew that we'd been playing around with this proof assistant Lean, so then he wrote up a challenge saying, hey, these guys working, this crowd working with the Lean proof assistant, if you really want to show that Lean can make an impact on the world, help me out because I'm stuck with this problem. And he wrote, I spent much of 2019 obsessed with this proof, almost getting crazy over it. And the proof was so complicated, he writes, I was essentially unable to keep all the objects in my RAM at the same time. So he's even sort of using computer metaphors to talk about his own brain. We worked on this problem, and what we saw is that this formalism, this really strict computer language, helps you manage this cognitive load, because once you've checked something in the computer, you no longer have to keep it in your working memory. You can actually trust that you don't have to see the entire proof all at once in your brain to be convinced that you got all the details right. And so we had this graph of all the components in the proof, and initially this entire graph was white, and then one by one components turned green as we filled them in, and there was much rejoicing when the final component turned green. So that's what we worked on in 2020 to 2022. And then this is all sort of work in Lean. There was very little AI involved. At the same time, ChatGPT was released, like that was 2022. That sort of coincided with the end of this project. And we were making jokes like, haha, it would be really fun if the AI could actually write some Lean code for us. Well, ta-da, 2024, AlphaProof by Google DeepMind took the world by storm, because this was the first time that an AI won a medal at the IMO. And this, for me, came completely unexpected. Like, I thought, okay, maybe 10 years from now. That's what I was thinking in sort of early 2024. Actually, in the summer, they did it. And this was a combination of AI, large language models, reinforcement learning, and Lean for verification. So they built this system. They used existing IMO problems, but there are only a few dozen of IMO problems. So that's not a large training set. So then they used large language models to automatically generate many, many variants, and they didn't really care whether the variants were really easy or very hard or somewhere in the middle, because if you generate loads of them, there will be good examples somewhere. And then they used this technique of reinforcement learning, which is sort of the training technique that was also used for AlphaGo and AlphaZero, to find the optimal sort of neural network based on this immense amount of training data. And they used that, so they, sorry, I missed a sentence. So they generated all those variants, but in the Lean language, and then they used reinforcement learning to learn proofs of all these variants, or counterexamples of all these variants. And so in this way, they combined formal verification in Lean and large language models and reinforcement learning on the AI side to build AlphaProof, which then went on to win a silver medal at the IMO. Good. This was all very exciting. But if you take a look, well, yeah, sorry, it's really small. You'll have to believe me. I'll read out the first line of the proof. So there's the statement, and then the first line of the proof, if you've really good eyesight, you can read this. It says, induction on 10 plus 2. So we're doing induction on the number 12. This actually basically doesn't do anything in Lean, so it's just meaningless. But anyway, it is a valid step. It just doesn't do anything. So it also doesn't really do any harm. But and that's why the proof could go on. Like there was no error message, but it also was complete. Like, what does it mean to do induction on the number 12? But anyway, after that, it does sensible things and it manages to finish the proof. But it just, this was also a sort of sign or moment where we realized, okay, these AIs are doing, like they don't think the way we think. It's behavior that we didn't expect and didn't foresee. Well, somehow it sometimes skips a slide. So then 2 years later, Terence Tao started a project because he wanted to know, the main thesis of this project was these machines are starting to show some signs that they can be helpful in mathematics. And he was really fascinated by the question, can they help us to do mathematics that was completely inaccessible before, that sort of, he calls it mathematics from Mars. And one reason we might not have been able to do it before was because we just couldn't throw enough resources at it. Collaborations in mathematics usually consist of 2, 3, 4, 5 people. Sometimes we have 10 people collaborating, and then we refer to the paper they write as the 10-author paper, which also means that apparently it never happens, and this is the unique instance of a 10-author paper. So he was like, can we use systems like Lean to collaborate with dozens of people at the same time? Because we can now crowdsource the trust. Like Lean gives this trust, this verification. So I don't need to know your credentials. If you produce valid Lean code, I can just trust the Lean code you wrote because Lean checks it line by line and it works. So we can suddenly collaborate with many people, even if we've never met them before. We don't even know their real name. We just met them on the internet. And we can also throw in computers of all sorts and kinds into this collaboration mix. AIs, traditional computer algebra systems, set solvers, many different kind of programs that can do computations or produce proofs. And so with a large team of dozens of contributors, they looked at loads of small algebraic laws. So you should think of like not the ordinary rules that the numbers satisfy that we're used to. Like we know that x times y equals y times x. Or we know that it doesn't really matter where you put parentheses. But now let's think of weird structures where those rules maybe don't apply, but other rules apply that say, I don't know, if you do a times b times c, then you're allowed to put the c at the front. And so you have some sort of cyclic reordering. Or maybe parentheses do matter, but only in a mild way, and things like that. So you can make loads of those rules, and basically if you have 4 variables that you can use and 4 multiplications that you can do, then you get roughly around 4,000 laws that you can create. And now which of these laws imply other laws? That was the question. And this is the type of question that a few years ago was just impossible to answer because we didn't have the tools to check all the proofs at scale. And sort of within days after launching the project, 99.99% of all cases were checked by computers. And then there were a handful of cases left that the computers didn't know how to tackle. And then the project went on for several months, where one by one, humans had to sit down and think really hard and construct crazy counterexamples or very ingenious proofs. But the cool thing is, all of this was formalized in Lean. Like both the human-invented proofs and all these cases that were settled by computers, everything was checked by Lean. And so there was this massive database of implications and proofs. And actually, just a few weeks ago, Tao launched another project saying we have this enormous amount of lean proofs that don't fit in our brain. So can we use AI to sort of find a cheat sheet that fits on one sheet of paper that explains which implications are true and which ones are not? And so maybe that's sort of a next evolution in this whole story. We can actually compress that information into something that we can then understand again. Very curious to see where that goes. Then in 2025, so now this is work done by Johannes Schmidt, who initially was supposed to give this lecture, but unfortunately he had to cancel. But he has been working a lot with AI in algebraic geometry and exploring what's possible, exploring what's not possible, developing benchmarks, and really testing these systems to see where they are, what they can do, and how they can be useful to us. And so he together with others, created this benchmark of problems, open problems, no proof known so far. And one of them was in his area of mathematics, algebraic geometry, on intersection theory on the moduli space of curves, whatever that means. But anyway, he was playing around with these AIs, asking them to try to solve these problems, and then one of them came back and said, I have a proof of this problem. And well, that happens more, that wasn't immediately surprising. But usually you would then spot a mistake and say, oh, well, you hallucinated a proof, but it's not actually correct. But this time he was reading the proof and he was like, okay, this actually looks plausible. This seems to make sense. And what I find really fascinating is he then wrote a paper where you can see in the margins there are bars next to the text. Some of them are orange, some of them are blue. And the parts where the bar is orange were written by AI, and the parts where the bar is blue were written by Johannes. And so this is really a human-AI collaboration. And it's a bit hard to see, but there are then, like, this second paragraph has a blue bar, but then in the formula, there's some parts that are orange. So actually, he wrote this and then asked the AI to review it, and the AI said, oh, there's actually a tiny mistake in the formula, let me fix it for you. And so, but you will also, in other parts of the paper, see that there are blue words in the text that was written by the AI, where Johannes said, okay, actually, I want to phrase this differently. So I think this is also a very honest way to communicate to your readers, here's how I've been making use of AI. And yeah, I think this is a really, I hope this example will see more use in the future. And the funny part, or the interesting part, is that the AI just did this proof from first principles, basically. It ignored all the existing theory on intersection theory on moduli spaces, but just started reasoning from abstract properties. Part of that proof was very combinatorial, and so Johannes decided, okay, this seems finicky and rather complicated. Let me just ask the AI to produce a lean proof of this combinatorial part of the argument, which the AI then went on to do. And back then, Johannes says he had never really written any lean code before himself, but he could read it. And so the AI wrote lean code. Johannes verified that, yes, the statement that this lean code is proving matches the statement that I'm interested in for this paper, and lean checked that the proof is correct. So that also gave him more confidence that really also the tricky part of the proof, where some complicated combinatorics was involved, was also watertight. So yeah, here we see a very nice example of human-AI collaboration. And so this is now 2025. We're just 3 years after the release of ChatGPT. Another example I want to talk about is the sphere packing project, which started, I don't know exactly when it started, so I'm not putting a year here, but it's been going on for some time. And so this was led by a group of 4 people, Chris Birkbeck, Sid Hariharan, Bhavik Mehta, and Xiao Li. And they collaborated with Marina Wiazowska to formalize her Fields Medal winning work on sphere packings into Lean. And yeah, so this was a project where they also invited many people to help out and contribute, and they also engaged a lot with people experimenting with AI to see how they could formalize all of this in Lean and learn how to use AI in that process. And then all of a sudden, there was an announcement just end of January, so this is now very recent, where an AI lab called Math Inc. Said, we've done it all. We've just completely formalized the entire proof. And yeah, this was quite a disheartening moment because sort of collaboration had broken down. They just, out of the blue, didn't collaborate with the other people, produced this gigantic proof of more than 200,000 lines of Lean code. And if you look at it, like we made fun of the IMO proofs by alpha proof, saying, oh, the proofs are looking weird. But, well, they still fit on a page, and it was like, okay, this is sort of a proof of concept, but we hope this will improve, etc. Now you have 200,000 lines of code of slop that are basically useless, except for the fact that they say, we formalized a proof. And so what we see here is an emphasis on speed and marketing stunts without really caring much about the mathematics and the mathematical community. The tagline of this Math Inc. company is solve math, solve everything. Yeah. Anyway, we're also in 2026 seeing really exciting examples. So here's another open problem. This was not just a random open problem. It's part of a pretty famous benchmark for testing AIs called Frontier Math. And this is the first open problem on that list that was just a few days ago solved by GPT 5.4. So yeah, there is a lot happening, and it's moving really fast. But we should also take a step back and think for a moment, like, where is all this heading? Is it going in a direction that we want, that we like? Where will this lead? What might this look like in 5 years or even 50 years? Well, of course, making predictions about what the world will look like 50 years from now is, I'm not actually going to do that. And even I'm not a prophet. I will not actually make predictions, but we should try to take stock of where we are and think about the future and how we want to engage with what's going on. So I want to think through 5 scenarios with you briefly. And the first scenario is, well, there was very rapid developments in AI in the past few years, but we're very close to a point where it will taper off. It's an S-curve, like we saw a really sharp incline, but now it's going to plateau. And what we'll have is AI tools that are very much like Mathematica, but a bit better. That's very comfortable, but I think it's a really bad basis for making strategic plans based on this scenario, because all the evidence we have is that it's not going to plateau in the near future. Maybe it's like chess. So maybe AI will sprint past the capabilities of fields medalists. But we'll just continue doing mathematics, just like people are still playing chess. People are still having loads of fun playing chess. We'll have loads of fun doing mathematics. But I like that scenario, but who's actually going to pay the bill if we want to all do mathematics, whereas people can just pay a machine to do it? So I don't know. Another option is AI gets really, really good and produces loads and loads and loads and loads of mathematics, and it's going to be our job to sort of find the needle in the haystack of all the mathematics that's being produced, like what is the mathematics that we actually care about. And so then sort of producing proofs becomes maybe a solved problem, but now finding the actual meaning is going to be the hard and tricky part. Like what is the stuff that we care about? And all this math that is being produced, what does it actually mean? And which parts are useful to us, etc. Scenario 4 is, right now we're seeing that these new models that have been released in the past few weeks, like GPT 5.4, Opus 4.6, are really a lot better than the models that were released 3 months ago. And those were a lot better than the models that were released 3 months before that. So there are also other models available that are so-called open weights models. You can download them, run them on your own hardware. But these models are a lot smaller, and their quality is also a lot less. They usually, at the moment, they lag behind the frontier models by roughly half a year, maybe a bit more. And if that pattern continues, then one scenario is that to do mathematics, you have to, like to do frontier mathematics, work on the exciting problems, you have to be at a leading institute at an elite university that has loads of money to pay for really expensive AI, and then you can work on the super exciting problems, and otherwise you're sort of left in the AI dust, and you can work on maybe interpreting some of the stuff that rolls out of these big labs, or refactoring it, or maintaining it, or working on some niche problems. And honestly, like, this happened before in parts of physics and biology. Like in experimental physics, it's not like mathematics until a few years ago, or maybe still even until now. If you have a blackboard and a piece of chalk and some good ideas, you can just go ahead and do mathematics. But in these lab sciences, it's, yeah, you really have to be in the right place, connected to the right people and the right sources of money, and that makes a big difference in what you can and cannot do. Another scenario is that this actually does democratize mathematics. These open weight models catch up with the frontier models. The models become so good and so cheap. Like if you look at the cost of using AI, this is declining super rapidly. And if that continues, like 2 or 3 years from now, we might just be running what currently needs a data center on our phones. Who knows? Like, this is not completely ridiculous. And so then anyone with a laptop and an internet connection can just do frontier mathematics using AI. And I think this is what we should fight for as a mathematical community. I think it's really important that we are part of the discussion, that we take a seat at the table and don't let the big tech companies decide our future. So as part of that, I'm very proud of having co-organized a workshop last fall with some brilliant people and a really, really interesting mix of audience members. So we had a bunch of mathematicians, but we then also had philosophers, historians, sociologists, And instead of sort of the standard math research workshop where people give lectures about their recent work and then people discuss over coffee the most recent developments and breakthroughs in area X of mathematics or subject Y, we spent a full week thinking about what does all these developments in mechanization of mathematics, what does that mean for the mathematics community? What does it mean for the future? Where are we? Where do we want to go? And if we sort of figure out where we want to go, how do we actually get there? And this is not something that was done only that week and we figured it out with a group of 50 people and now we'll just do that. This is something we should do all together as a math community. So I do want to share a little bit of the things that we talked about during that week. Every day we asked everyone to sort of submit questions, ideas, suggestions, etc. And we collected those, then people discussed sort of clusters of those topics in breakout rooms and digested that down into some recommendations and focus areas. And then towards the end of the week, we collected all of those together and did one more round of digestions. And we basically brought this down to 5 focus areas where we have some sort of recommendations or call to actions. And so we've written a report on that which should appear on the archive hopefully this week. And I think we sort of tried to craft these recommendations carefully. So I'm going to read them out loud because I won't be able to actually do them justice if I just try to cook them up at the spot. So the first one is about our values. And there we say we should ensure that the development and adoption of new technologies in mathematics remain firmly rooted in our own epistemic and aesthetic values, diverse as they are, rather than driven by the internal logic of those technologies or the commercial interests of their developers. Then on the future of mathematical practice, we should engage collectively and alongside our students with the question of how our relationship to mathematics will change if computers are able to perform many of the day-to-day tasks of current mathematical practice. With respect to teaching and education, we encourage everyone to review the mathematical curriculum to emphasize a broader range of skills, including posing problems, communicating ideas, and evaluating logical arguments. So instead of a focus on calculation and producing proofs, we should diversify what we teach our students. Then number 4, on the topic of technology, we should build academically governed technological infrastructure with open source code, transparent decision making, and community oversight. And I think this is really important to move here as a community and to not just let everything be, well, decided by for-profit capitalist big tech companies. And finally, on the topic of norms, ethics, and governance, we should, as a community, develop a living statement of ethical principles to guide academic mathematicians and, well, mathematicians in general in their interactions with AI systems and the developers. So, yeah, this is a call to action to all of you because a lot is happening right now, and I think everyone who has an interest in mathematics should engage with what I think is, like, we've built many wonderful things as a math community over the past 2,000 years, and math has always been a conversation between people who want to understand the world that shouldn't change. So that being said, life is more than computers and mathematics. Go for a run, sing a song, plant an apple tree.
Thank you very much, Johan. I allow for a couple of questions. And yeah, there's another microphone, other mic. There's
Could you stand up?
I know. Yeah.
Hi, my question is more about like the proof, the very long computer, like AI-generated lean proof. What went wrong with it? Did it end up proving a different problem, or did it just say it was wrong? Like, just what was wrong?
So the question is about this super long lean proof produced by Math Inc. on this sphere packing problem. And the question is what went wrong there? So from a technical point of view, nothing went wrong. Like lean confirmed this is a proof of the statement that they were trying to prove. What I think went wrong is much more of a sociological nature. Like maths has mostly always been done out in the open, where people are happy to share what they're working on and discuss with others and collaborate. And I mean, there are exceptions, but there are exceptions. And here we see a group of people, mostly young people, working on this project, and then a multi-million-dollar company just barging in saying, "Bomb, finish the project, we take the credit." And so it's not directly a math, not in a technical sense a math problem. They proved the right statement, but it's like this goes against the values that we've had as a math community. It's a social problem. Yeah.
Arnoud,
Is AI basically applicable universally to all mathematics, or are there parts where it is especially strong or especially weak?
Yeah, that's a good question. At the moment, things are moving so fast. There are areas where AI is at the moment stronger, and there are areas where AI is maybe less strong right now. But if we extrapolate the developments from the past 2-3 years, then in 1 or 2 years, it will be useful across the board. And so the same is true for lean. Like, if you want to formalize a proof in lean, then everything that is used in the proof, sort of all the prerequisites, also need to be formalized in lean if you want this to be useful. So in some areas of mathematics, a lot has already been formalized in lean. In other parts, there's still a lot missing. But yeah, this is sort of a rising sea. And so the answer is, at the moment, it varies. In some areas, you can make more use of AI and more use of lean. In other areas, it's still less, but yeah. So I would say in algebra and number theory, you can do quite a lot, especially with lean. PDEs, for example, there's still very little. With AIs, it depends on, do you want the AI to, like, do you want the results of the AI to be checked by lean? Well, then the same restrictions apply. If you're happy with sort of stream of consciousness text, then yeah, I would say it's already quite useful across the board.
Okay, there was one more question, I think. Yes?
It's kind of comment or question, clarification about your answer for the first question. But isn't the same happening with actually gold medal for Math Olympiads, that there is a competition sponsored by XTX, but none of the companies that claimed that have won gold was not participating in the event. They just sit there the whole night, do something, and that claim, oh, we did it. Isn't it the same?
So, yeah, for context, okay, so there is the Math Olympiad, which is a yearly competition for high school students, where you just get questions in English or whatever language you want to do the competition in. The questions are translated, and you write it, as a high school student, you write your answers in the same language, and they're graded by a committee. And so AI companies have been taking those questions, having AI produce the answers, and then also grade them by committee. Some AIs produce lean code, and then lean can check the answer. And then next to that, this company XTX created a challenge saying, if you can win a gold medal at the IMO using open source software and open weights models, then you win this big prize. And it's true that like the big AI labs are not participating in that at all because they don't want to release, like they don't want to make their models open weights. Smaller companies have been working on that, and I think it's actually very likely that this challenge will be completed this year. But we have to see, like in a few months we will know. But to answer your question, like, yeah, so the big AI labs are not interested in that challenge because it sort of undercuts their business model.
One more question there. And one more there. They are the last two questions.
Yeah, okay. I should say, I think it's a really good challenge.
Just clarifies the XTX challenge, not IMO.
The AIMO challenge by XTX, yes. Yeah.
Thank you for a very clear presentation. My question is about trying to grasp the impact of this technological revolution. Let's say analogous to a computer programmer who, with AI that can generate computer code, doesn't need to do that by himself, but is relegated maybe to a role of evaluating code, like you mentioned, mathematicians maybe evaluating proofs. If that goes on for a generation, then you could envision that the new generation growing up who didn't learn to program by hand no longer maybe has the skills to do the proper evaluation because you need the experience of actually doing it yourself. So how big will this step be, do you think, of AI doing mathematics? Is it a similar step to we don't need to do, since we have calculators, we don't need to do arithmetic in our minds, but we do that by calculation and we, do more abstract stuff. But now that AI is doing the more abstract stuff as well, will there be nothing left? Or where do we put the magnitude of the change relating to a human skill?
Yeah, I think that's an excellent question, and honestly, I don't feel qualified to answer it. Because as you say, there are sort of two scenarios. One where you have this sort of, we completely lose skills, and not just in mathematics. Like this is a problem for all of society and education. Like how are kids going to learn things 5-10 years from now if AI is used everywhere? We just don't really know. But then you also point out that this is sort of not the first time we're seeing a technological revolution. You give the example of calculations and calculators, but also in the Industrial Revolution, people had all sorts of really fine-tuned skills in crafting, etc., that now are, that were completely replaced by machines doing those jobs, but worse. Right? But we learned to live with worse. We are happy with IKEA chairs instead of handcrafted rocking chairs. And some people still build handcrafted rocking chairs, and they get a lot of joy out of that. But it's not the mass product. So, yeah, I do think we humans are a sturdy bunch, and so I want to be hopeful. We'll probably learn to live with this, but how exactly that will look like, I don't know.
There was one more question in the end. Yes? Can you go there?
All right. So I have a question kind of relating to your scenarios. Whether there's, let's say, a more centralized AI, or whether we can all use our personal AIs, maybe they're more efficient. So in your experience, do you feel that there's a single, let's say, intelligence factor, and the more data goes into the AI, the more parameters, the better it is for math? Or if you see the need for, let's say, different AIs with different architectures, different data, etc., for different areas of math?
So again, things are moving really fast. So in the past few years, maybe, we've seen that specialized models sometimes for a little time outperform the generalist models, but then the next generation of the generalist models just, again, sprints past the specialized models. And at the moment, it seems like the really super large generalist models like Opus by Anthropic or GPT by OpenAI, it doesn't matter what you throw at them, they're just better than the specialized models. Whether that's still true half a year from now, I find impossible to predict.
Somebody has to do the throwing.
Sure.
Okay, I think we should quit the questions now. During the reception, you can try to grab him and ask questions. Johan, I'd like to thank you very much for this very interesting lecture.
Thank you.
Small token of you.
Thanks.
So you are all invited downstairs for the reception. See you next year.
Dankjewel.
Ja, ging ietsje sneller dan ik had verwacht.
Ja,